In this video, we will introduce the Wire Embedding 3D Printer, a project for Applied Science 459 at UBC. My name is Jacob Bayless, and my team members are Mo Chen and Bing Dai.
First, a brief introduction to the RepRap project. The RepRap project, short for Replicating Rapid Prototyper, began in 2005 to develop an open-source 3D printer. Furthermore, the 3D printer is designed as a self-replicating machine. The RepRap is a community project, and anyone can join, so we did. The RepRap has a plastic extruder mounted on a Cartesian 3D robot. The extruder extrudes a thermoplastic filament like a hot glue gun. The plastic being printed in this video is PLA, a biodegradable polymer.
The RepRap can already produce all of its own plastic parts, reproducing the majority of the machine's structure. It cannot, however, produce its electronics. Many efforts are underway to improve the RepRap, such as a heated bed, printable ceramics, and a milling tool. In January 2010, the Foresight Nanotech Institute announced its Kartik Gata Humanitarian Innovation Prize. This award was created to develop self-replicating rapid prototypers like the RepRap, and includes an interim prize of up to $20,000 and a grand prize of up to $80,000. Importantly, to win, the machine must be able to print usefully electrically conductive materials and electronic circuit boards.
Efforts to achieve this have already begun. In April 2009, Rhys Jones demonstrated the first RepRap circuit, printed out of solder. Another method is to have low melting point alloys flow into printed channels. But copper is a preferred conductor for electronics applications and cannot be melted. We therefore sought to create a tool that prints wire directly. As an added bonus, this same tool might print wires from steel or even nitinol for mechanical purpose like joints and flexures.
Bonding wire to plastic is a crucial step in our process. We observed that the RepRap's thermoplastic forms a tenacious bond with metal wires when heated. This worked for copper and also steel wires, even enamel-coated magnet wire. Next, we built a mock-up of our device and operated it by hand on the benchtop. We were able to determine operating variables, such as what temperature the tip should reach in order to create the bond. We also tried different algorithms for printing wire patterns to see what pattern of heating, cooling, and motion worked best. The final design of the wire printing mechanism is composed of 3 parts, starting with a mechanical pencil. We used a standard 0.5 mm pencil to feed the wire forward from the spool before it's bonded to the plastic. The pencil is actuated by a servo motor, which clicks it by pulling on a stiff cord. This proved to be quite successful.
Because a wire doesn't melt, it's necessary to cut it when finished. Our cutter design was a brass insert that fit into a steel tube, with holes drilled to line up. A solenoid then tugs the insert, sliding the hose out of alignment and shearing the wire. Unfortunately, this method failed. The stainless tube's mounting was not stiff, so rather than breaking the wire, the solenoid ended up pulling the entire tube over. This design was unsuccessful. We will have to find a better way.
The heater forms the bond between the wire and plastic. It is designed with a cone-shaped taper to minimize unwanted heat transfer, but it is otherwise similar to the plastic extruder on the RepRap. Nichrome wire forms the heating element, surrounded by a fiberglass insulator. We tested versions from aluminum and stainless steel and found both to be successful.
On the software end, G-code is a machine tool command language that dictates how the RepRap moves to print each part. We wrote a MATLAB script to generate customized G-code for different patterns, such as spirals. This greatly reduced the effort involved in printing new designs.
Here is the whole wire printing mechanism put together. A wire spool sits at the top, earning the nickname SpoolHead, or Spool Printing Tool Head. And here are the results. We successfully printed 2 wire patterns, a spiral and a square.
Here is a quick video to show how the spiral was printed, using a plastic guide laid down by the plastic extruder. Note that this video is sped up. In reality, the initial and final bonds take time due to the temperature change.